Okay, I'm continuing to think aloud as I complete the practice final exam, part 1. And we're just getting into Unit 2, Mod 2, the section on translations. And again, all of these 1-point starred questions are going to be pretty much identical on the actual final exam, especially the ones that are definitions. There might be slight changes, but they'll be pretty similar, and the definitions will be exactly the same. Okay, so here, what are the definitions? So a statement that can't be broken down into other simpler statements, a statement that doesn't have any subparts or smaller parts that are themselves standalone statements, / doesn't contain any statement operators. These are all ways of identifying atomic statements. An operation that creates a compound statement from one or more other statements. Not necessarily atomic. That's what operators do. So when you use conjunction, disjunction, if-then, negation, what you're doing is creating a compound statement from other statements, not necessarily atomic ones, from any two statements. Okay, next, a statement that can be broken down into other simpler statements. It has one or more parts that are themselves statements, contains at least one statement operator. These are 3 different ways of identifying compound statements. And the statement operator that has in its range the largest component or components in a compound statement. Okay, that's the main operator, and this definition is confusing if you don't already know what a main operator is. And since there's a question coming about main operators, we'll explain that in more detail in a moment, or review it, rather. Okay, which of the following are statement operators that we're using? Hopefully this one's pretty simple. Conjunction, negation, disjunction, conditional. Okay, so what's the main operator? Remember our definition above here. So the statement operator that has in its range the largest component or components. What does that mean? What is the range of an operator? Well, the range of this operator is this. The range of this operator is this. Basically think, what does it apply to? That's roughly right. So what does the conjunction apply to here? It applies to P and Q. What does the negation apply to? It applies to this whole thing. So this is the largest component, right? It's got in its range the largest component. Beyond that, you can just think, this is a lot like math, identifying the main operator in math. So we've got, it's the thing you would evaluate last, working from inside to out. Okay, so what's the main operator here in B? Well, the inside, we've got this applies to this and this applies to this, and this applies to everything else in the statement. So this is the main operator. What about for C? And this only applies to P and Q, this applies to the whole thing, this only applies to R, this applies to everything else in the statement. And finally, what's the main operator here? Hopefully we can tell, it's this conjunction, because the conjunction applies to everything in the statement. What does it mean to say that statement operators are truth functional? Is it truth is a function within a, this is gibberish, it's not this. Statement operators turn non-statements into statements? No, that's gibberish. Statement operators turn sentences in symbolic notation into ordinary language sentences? That's gibberish. This is just false. It's E. The truth or falsity of a compound statement, sorry about the typo here, depends on the truth or falsity of its component statements and the meanings of the statement operators used to construct it. When you encountered the initial symbol game section where we introduced translations, this was really emphasized, especially on the made-up ones. The point is that all of our operators, I think we used, make up any operator you want. This is called the cat operator. And it's a two-place operator. It takes inputs. Let's call the inputs, we'll say X and Y can be inputs. And it outputs what? You could make a star is what it outputs. You can literally specify anything. The point is that this is a function because it takes inputs and outputs something. And for our operators, we have special operators like conjunction. It takes certain kinds of inputs. It takes statements, or rather their truth values, truth or falsity, as inputs, and it outputs a truth value, true or false. And to say that this is a truth functional operator means that the truth value of the whole thing, of the output, is a function of the truth values of the input. So the answer is E. Okay, which of the following are atomic statements from the following passage? So in order to identify the atomic statements, I recommend focusing on identifying operator words. So Misa will go to the show only if, immediately seeing an only if here, only if she has the time and money, and is an operator word. She has the money, but is another conjunction word. She doesn't have the time. That's a negation. So that is a conclusion indicator word and not an operator. She won't go to the show. Another negation. Now I'm going to double check for negations because those are the easiest things to miss. I don't think I have missed any. And so now I'm going to try to identify what are the atomic statements being created with these operator words. So Misa will go to the show, seems like one, only if Misa has the time, and we could extend this if we were to speak like a robot, Misa has the money. Misa will go to the show, Misa has the time, Misa has the money. She, Misa, has the money, but she, Misa, it's not the case that Misa has the time. So it is not the case that Misa will go to the show. So Misa will go to the show, Misa has the money, and Misa has the time. The other way to think about answering the identify the atomic statements kind of question is to go through the answers and just decide whether or not they contain any operator words and make sure they're full sentences. So she has the time and the money. That can't be right because there's an and word. She doesn't have the time, can't be an atomic statement. She won't go to the show, can't be atomic. She has the time and the money, can't be atomic. Only if she has the time and the money, one, it contains an operator word, two, it's not a complete sentence. So there's sort of two ways to approach these. Translate the following statement into symbolic notation. Again, start by identifying operator words. Bharat went to Yale only if his twin brother didn't. And then identify the atomic statements. Well, these were already identified for us. That's helpful. So Bharat went to Yale. Bharat's twin brother went to Yale. And so the next step is to translate in steps. Bharat went to Yale. And I sort of just leave the operator words in English and replace the atomic statement next. Only if his twin brother didn't, I'm going to say move that negation out to the front. Only if not, his brother did go to Yale. So B, only if not T. The question now is, how do we translate only if? Remember, there's a difference between if and only if. Whatever comes after an if, a plain old if, is the antecedent of the conditional, right? So antecedent, consequent. If it's a plain old if, it goes here. But whatever comes after an only if goes here, is the consequent. So here, not T is what comes after the only if, and then the other part is the antecedent. So this is our final answer. If B, then T. Assume for the sake of argument that Bharat and his brother both went to Yale, i.e., assume that B and T are both true. So let's determine the truth value of the above statement. So the starting place is this. And we're going to assume that they are both true. So we'll let B have the truth value T, and Bharat's twin brother, it's perhaps weird that the variable we used to stand for the statement was T, and now its truth value is T, but we'll just go with it. And now we'll figure out the truth value of this statement. So not T is F, and now we have if T then F, and that is the only time a conditional is false, when the antecedent is true and the consequent is false. So that statement is false when both statements have the truth value T, are true. Complete the truth table for the same statement. Okay, so ultimately we want to know the truth values for our complete statement of interest, the one we translated and started with here. And then in order to do that, we need to make sure every part of the statement is in the table. B's already in, so we need to make sure not T is in. T is already in. We can set up the table. Okay, so these are in alphabetical order. The T's and F's are filled in correctly. Now we can fill in the column for not T. To do that, we look at the column for T. Wherever T is true, not T is false, and vice versa. And so now to figure out this, we're looking at the antecedent and the consequent. In this case, they're in the same order. That's nice. The only time a conditional is false is when the antecedent is true and the consequent is false. So I'm just going to look for that case first. Antecedent is true, consequent is false. So here's a row where they're false. T, T, F, 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 T. So that's the only one where it's false. Everything else will be true. Okay, so we filled in the truth table, and what does this tell us? So above, we said just assume B and T are both true. That's like saying assume row 1 is the case, that B and T are both true. In this row, in this case, if this is right, then the whole conditional will be F. But of course, there were 3 other options, and that's what the table tells us, all of the options. So this is stipulating one possibility, and this is all of the possibilities. And the point of the table is to keep track. That's all the table is doing, is keeping track. It's a method for keeping track. Okay, translate the following statement into symbolic notation. Neither the cake nor the donuts are gluten-free, but the ice cream is. So I'm going to circle operator words. I see a neither nor, and I know that's a special one to translate. Neither nor, but that's another word for conjunction. The ice cream is. And we've been given a key. So neither the cake is gluten-free nor the donuts are gluten-free, and the ice cream is gluten-free, if we were to speak like robots. So I'm going to go neither C nor D and I. The real tricky part here is how do we translate neither nor? And is easy. We've got and I, and we know that this part, the comma, helps us keep everything together, that this part goes together. How do we translate neither nor? there's two ways to think about it. One is not either C or D. The logically equivalent way to translate it would be not C and not D. This would be logically equivalent, as in we can do a truth table to show that these will have the same truth values on every row of the table. But the most natural way to do it, neither nor, is not either. That's what the words literally are saying here, not either. So let's translate it that way. So now that we've got not C or D and I, and that is our final translation. Okay, so assume for the sake of argument that the cake and the donuts are not gluten-free, but the ice cream is. Basically assume C and D are both false and I is true. Let's determine the truth value of the above. Well, all we're doing is just start with a statement, C or D and I, and then follow what's being stipulated here. So C and D are both false, assume that, and I is true. And then just work our way from inside out. So a conjunction of F and F is F. The negation of F is T. And the conjunction of T and T is T. So the final truth value for the statement will be T. Now let's complete a truth table for this same statement. Ultimately, we want to have this as our final row or column. What do we need before that? Well, I is already in the table, so that's good. And the other part is not C or D. Okay. So both parts of both conjuncts are in the table. Now what about this one? In order to figure out the negation of C or D, I need to have C or D. Now its part, the negation's part, is in the table, and these are both atomic statements. They're in the table. We're ready to go. Okay, I didn't apportion my column size appropriately, but it doesn't matter. Okay, so when is a disjunction false? Because that's the special case. There's only one case where a disjunction is false, and that's when both of the disjuncts are false. So let's just look for all the places that we're looking at columns C and D here. Let's just look for all the rows where they're both false. TT, TT, TF, TF, FT, FT. Here they are. It's just these two rows. So we'll fill those in, and then everything else is T. Okay, now we're looking at the next column here, and this is the negation of this column. So we need to look at this column, and wherever it says T, we put F, and vice versa. So row 1 is T. Okay, now this is a conjunction of, here's one conjunct, and here's the other conjunct. And so we got to look at these two columns, and when is a conjunction true? There's only one case where a conjunction is true, and that is when both conjuncts are true. So let's just see if there are any rows where both of these columns are true. TF, 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 FT, FT. There's no row where they're both true. So there's no T row. They're all F rows. I've made a mistake. Do you know what the mistake is? Right, I was looking at the last two columns I made and not the actual conjunction. This is the other conjunct. So I need to look at the columns for the negation of C or D and the column for I. not just the last two columns I made. Okay, so now, is there a row where both conjuncts are true? So row 1, we've got T and F, 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 T, F, 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 T, F, 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 T, T, there's one, F, T. Okay, that is our final complete truth table. And so what does this have to do with the previous question? Well, previously we said, let's just stipulate that C and D are both false and I is true. Well, that's one of the possible combos of truth values they could have, where C and D are both false and I is true. So we were looking at row 7 here. And when C and D are both false and I is true, the truth value of the whole thing is true. So what we stipulated here is essentially what we've captured on row 7. But again, this is one possible option, and the table is how we keep track of all of the possible options. Why does the above table require 8 rows? What is the point of the rows? So as I've been emphasizing, the table is merely for keeping track of things. Keeping track of what? The possible truth values for the atomic statements. So when there are 3 atomic statements, there are 8 possible combos of truth values. They could all be true, they could all be false, and here are all the ones in between. Okay, now we're going to move on to using truth tables to evaluate relationships between statements. So let's let alpha, beta, and gamma be any statements, and the reason we're using Greek letters is because we're talking about any statements and not necessarily atomic statements. So what is the definition of equivalence? Two statements are equivalent if and only if they have the same truth value on every row. For every assignment of truth values to the atomic statements, they have the same truth value. One statement implies another statement if and only if in other words, there's no counterexample row. There's no row where alpha is true and beta is false. Two or more statements jointly imply some other statement if and only if. Same exact definition, except for instead of if alpha is true, it's if alpha and beta are true, then gamma must also be true. It's impossible that the statements doing the implying are both true or all true, and yet the statement being implied, gamma, is false. Okay, and we are defining validity in terms of joint implication. So an argument is valid if and only if the premises jointly imply the conclusion. Okay, so now let's do truth tables in order to actually evaluate some of these relationships that we've just defined. So let's construct a truth table for the following 4 statements. This isn't an argument, this is just 4 statements, and we're going to put them all in a single truth table, a joint truth table. So start with the atomic statements, and just like a single statement, you're just going to count the number of different letters across all the statements. And there's only P's and Q's involved here, and that's why these are the atomic statements. And now we can immediately fill in the columns for the atomic statements, because they get filled in the same every time, and the point of the rows is just to get all of the possible combos. So we'll do halvesies, TTFF, and then TFTF. We'll do it the same way every time to ensure we get all of the combos and that all of your truth tables look the same and get auto-graded correctly. Okay, so now to figure out the possible values for not P, we need to look at the column for P. Wherever P is true, not P is false, and vice versa. Next, we're doing the conjunction of P and Q, and there's only one way a conjunction can be true, and that's when both conjuncts are true. The only row where P and Q are both true is row 1. So we'll put that as T, and then we can automatically fill in the rest as F's. And then P or Q. So again, looking at the same two columns, but this time we're doing or. There's only one case where a disjunction is false, when both disjuncts are false, and that's only on row 4 here. So every other row is T. Okay, we've completed our table, so now we can use it to answer questions about relationships between statements. So are statements 1 and 2 equivalent? Do they have the same truth value on every row? TT, FT, nope. There's at least one row where they don't, so no. Does statement 1 imply statement 4? Is there any row where statement 1 is true and 4 is false? TT, FF, FT, FT. No. There is no row where 1 is true and T is false, which means 1 does imply statement 4. Yes. Think of it as there's no counterexample row, no TF row, which means yes, it does imply. Does statement 1 imply statement 2? Is there any row where 1 is true and yet 2 is false? TT, FT, FT. Yes, there is. Oh wait, no, I just erased part of it. Okay, make sure your handwriting is good. This won't be a problem when you're typing stuff. There is no row where 1 is true and 2 is false. Does 2 imply statement 4? Is there any row where 2 is true but 4 is false? T, T, T. Here's one. Sorry, I'm making a bunch of typos here. I said yes, but then I wrote no. Finally, do 2 and 3 jointly imply statement 4? So here we're looking, is there any row where these two are both true, and yet this is F? They aren't even both true on this row, not both true. Here's one where they're both true, and this is true. Okay, that's fine. Not both true. All right, yes, because there's no counterexample row. There's no case where 2 and 3 are true, but 4 is false. And if you stop to think about it, these should also make sense. So this is saying, let's let P be, I have a penny, and Q be, I have a quarter. This is like saying, I have a penny and a quarter, so I've got 26 cents. And this one says, I have either a penny or a quarter. Well, what are the options? Either I've got 1 cent, I've got 25 cents, or I've got both. I've got 26 cents. So any of those could be the case. Are those the same statement? No. Like, they're just not. That should be obvious, right? One is they're both true, and one is one could be true, but the other could be false, and vice versa. So definitely not. Does 1 imply statement 4? So if I know that I have a penny and a quarter, do I also know that I have at least one or the other? Yes, if I have both, then I have at least one. So 1 implies 2, and that makes sense. That was this one. I'm sorry, I'm going out of order. Does 1 imply 4? This says I've got a penny and a quarter, and this says I have a quarter. Well, if I have a penny and a quarter, that implies that I have a quarter, right? I can't, if this is true, this would also have to be true. So that makes sense. And then does 2 imply statement 4? Well, this says I have one or the other. I have either a penny or a quarter. Does it follow that I have a quarter? Well, no, because this, the way this is true, could be that I just have a penny. If I just have a penny, this would be true, but this would be false. So no, doesn't imply. And then finally, do 2 and 3 imply statement 4? And now that we've done the proof material, hopefully you can see that this is actually a case of disjunctive syllogism. If I know that I've got either a penny or a quarter, but I don't have a penny, well then I've got to have the quarter. If these two are both true, this has to be true. Okay. Next, we're going to translate arguments into symbolic notation, use a truth table to show that the argument is valid, and then transition into the proof method. We can also use the proof method to show it's valid, and then we have a bunch of proofs to do, and I'll do those in a separate video. So let's finish up our translation and truth table focus. Okay, so we're translating arguments here, which means you have to provide a key and put it in standard form. I have either a cat or a dog. If I have a dog, then I have a yard, but I don't have a yard, thus I have a cat. So I have a cat, forgive my sloppiness. I have a dog, I have a yard. Write with complete sentences. Okay, translation. I have either a cat or a dog. If I have a dog, then I have a yard, but when things start with conjunctions, just ignore them. But I don't have a yard, thus that is a conclusion indicator word. I have a cat. So the conclusion is clearly I have a cat. One is I have either a cat or a dog. Two is if I have a dog, then I have a yard. And 3 is I don't have a yard. Okay, so let's use the truth table method to show that this is a valid argument. And we're told it's valid up front, I believe. Well, it will be, because otherwise we won't be able to do a proof. We can use truth tables to show that an argument is valid or invalid, but we can only use proofs to show that an argument is valid. Okay, so let's start by counting the number of atomic statements. How many are there? There's 3 different letters, so there's 3 different atomic statements, and put them in alphabetical order. Next, we need to make sure that every part of our argument is in the table. Here's premise 3. Here's premise 1. And here's premise 2. And finally, here's the conclusion. Now let's fill in the truth values for the atomic statements. We don't need to know anything to do this, except that there are 8 rows. Start with halvesies, TTT, FFF. Then we'll sort of cut that in half. Then cut it in half again. Okay, so we've got every combo. Now we're going to, wherever Y is T, not Y is F, and vice versa. Next, we're looking at the disjunction of C or D, so we have to look at these columns. A disjunction is false When both parts are false, that's the only time it's false. Every other combo of truth values is true. And the only place this is false is on rows 7 and 8. So I'll fill those in, and then just fill in t's automatically. Finally, D and Y, and they're in the same order, so that's helpful. They're not always in the same order. Make sure you're looking at the antecedent and the consequent, and not just the order. Okay, so the only time a conditional statement is false is when the antecedent is true and the consequent is false. Here's a row where that's the case, TF. And here's another row where that's the case. So these are the only rows where this conditional is false. Every other row it will be true. We've filled in our table, and now we need to use the table to show that the argument is valid. So if an argument is valid, then if the premises are all true, the conclusion must be true. It's impossible that the premises are all true and yet the conclusion is false. In other words, there can't be a counterexample row or a problem row. Think of it as looking for problems. No problem, it's valid. Okay, so let's just start by identifying where the premises are all true. And again, premise 1, premise 2, premise 3. Row 1, no. 2, no. 3, no. Here's a row where they're all true. Next one, nope, 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 nope. So there's only one row where they're all true, and on this row, the conclusion is true. And so what we have found is not a problem, which means it's valid. Why? No counterexample row. If the premises are true, the conclusion must be true. It's impossible for the premises to be true and the conclusion is false. That's what it means to have not found a counterexample row. And now we can use the proof method to prove that the argument is valid. So let's just take the same thing we've translated above. So C or D. If D, then Y, not Y. And we'll move the conclusion up and out of the way because now our goal is to prove it. There's two ways to go about a proof. One is to work backwards from the conclusion. The other is to just do things you see. And with a short proof, just doing things you see will probably work. Okay, so if you don't see anything, then what? Well, then you can just start trying to apply rules and just go in order, right? So for example, I want to apply disjunctive syllogism. I'm looking at premise 1, it's a disjunction. Can I apply disjunctive syllogism? Well, to apply that, I would need to have not C or not D, and I don't, so that's not promising. What about modus ponens? I've got a conditional. What would you need in order to use modus ponens? You'd need to have D, but we don't, so that's not an option. What about modus tollens, the other conditional? We've got a conditional. What would you need? You need the negation of the consequent, which is not Y. Oh, snap, we've got that. So, what can you conclude if you have a conditional and you have the negation of the consequent? You can conclude the negation of the antecedent, and we'll cite the lines we were looking at, 2 and 3, and the rule that we used, modus tollens. Now we have a new thing to work with, and we were just saying we've got a disjunction. If we had either not C or not D, we could use DS. Well, we just got not D. So we'll use disjunctive syllogism, C or D, not D. So we'll infer C. We'll cite lines 1 and 4, DS. And that is our conclusion. A proof is done when you have the conclusion on the last line and you have used the rules correctly. That's all there is to full credit on a proof. And if you want to be extra fancy when you finish a proof, you can write QED. And there's a bunch more proofs. I will continue doing proofs in the final video for Final Exam Part 1 practice.